Hi, everybody. This is Mr. Karlovsky, and we're going to move on to the real meat of this limits chapter, which is how to find limits algebraically, meaning no longer just from a graph, no longer from a table, but from an expression, an algebraic expression, a function, something like that. All right, so here we go. All right. So the first batch I'm going to go through really quick is that it says if a function is continuous at the x equals c value, then the limit at the c value, or as you approach the c value, is just f of c. So these first three examples are very straightforward. What's the limit as x approaches 3 of 7x minus 11? Well, if I know that 7x minus 11 is nothing, there's nothing wrong with that function, I can just straight up plug in 3 into the expression. And so the limit equals, what's that, 21 minus 11 equals 10. That's how easy a limit from an expression can be. Let's do the next one. The limit as x approaches pi of the cosine of x minus pi over 2. We know cosine is a continuous function, so let's just straight up plug in. Well, that would just be the cosine of pi minus pi over 2. And that's the cosine of pi over 2. And hopefully you haven't forgotten your unit circle values. The cosine of pi over 2 is 0. All right, and then finally number 3, the limit as x approaches 5 of the log base 9 of 5x plus 2. Just want to review some log stuff here. Well, log functions, although there is a domain restriction, but as long as our x value is in the domain, it is continuous. So that's the log base 9 of 5 times 5 plus 2. And so, my answer is the log base 9 of 27. And really, that's the answer. But hey, do you remember what that is? What is the log base 9 of 27? Well, if we pretend that that's some number x, then we would have 9 to the x equals 27. That's 3 squared, so 3 to the 2x equals 3 to the third. And so 2x must equal 3, so that value is 3 halves. All right, so that was just kind of some fun to review logs. But basically, yeah, the simplest limit is where you just plug in the value that x is approaching. And guess what? Those don't happen all that often. So now the next major chunk, we're going to look at what happens when it's not that easy, when there are either discontinuities or other things going on that don't allow us to just simply plug and chug. So let's look at the next major chunk. So now it says if a function is not continuous at x equals c, then there are several ways. And that's what we're going to do. You really need to just follow along on these problems, and we're going to see a whole bunch of techniques. Some are easier than others, and let's have a look. So look at number 4 here. The limit as x approaches 2 of 3 over x minus 2. Now, my instinct might be to just plug in 2, and if I did that, I would get 3 over 0. And as you know, 3 over 0 is not a number. So you should never write the answer 3 over 0. Your answer, and again, I probably wouldn't even do this work. I'm just going to say that the answer does not exist. There must not be a limit at x equals 2, or as x approaches 2, if I were to say that perfectly. All right, so again, the answer does not exist. Don't leave your answer as 3 over 0. Don't say infinity. That's not quite the same thing. Yes, yeah, don't say infinity. Don't say infinity. Now, I do want to ask, though, why is there no limit there? Well, this graph, I hope, is something kind of familiar to you, right? 3 over x minus 2, that's just a rational function, and back when we did this, we would have seen that there was a vertical asymptote at x equals 2. And so off the top of my head, I don't know if it's going up or down, although I guess I'm pretty sure if I plugged in 1, that would be negative. So actually, yeah, the real graph does this, but we don't really even need to care about that. But the fact that there's a vertical asymptote tells me that there is not a limit at that as x approaches 2. Okay, so that's a pretty good one. Now let's look at number 5. The limit as x approaches 1 of the inverse tangent of x over the natural log of x. Yeah, I wanted you to see these values. Well, again, my first step might be to just straight up plug in the value. Hopefully we'll get lucky and we won't have any issues. All right, the inverse tangent of 1. Do you remember where is tangent 1? That was here at pi over 4. And then what's the natural log of 1? Wait, e to what power gives me 1? 0. So again, we have our denominator equals 0, and so our answer is does not exist. All right, I have no idea what that graph looks like, but this shows that when you plug in 1, I get pi over 4 over 0, so that limit does not exist. All right, and so these first two examples, I'm just going to kind of make a quick note here that just says when you get, I'm just going to say a number over 0. Okay, so at any number over 0, well, almost any number, hint, hint, coming up. When you get any number over 0, the limit does not exist. Simple as that. So again, those are really easy ones. Unfortunately, those don't happen, all the time. So we've got, easy and medium ones. But yeah, if I plug in and just get a number over 0, the limit does not exist. And the only number that we're going to have to worry about now is 0. What happens when I get 0 over 0? And that's what the rest of the sheet is pretty much going to talk about. Okay, so let's have a look at this expression. The limit as x approaches 4 of 2x minus 8 over x squared minus x minus 12. Now, I might just go ahead and plug in 4, although you will realize that you won't want to do that. But if I just go, oh, it's so easy, let's just plug in 4 squared minus 4 minus 12. And spoiler alert, guess what? You get 0 over 0. Oh my gosh, what to do? Okay, so then you realize, all right, we got to do something else. Hey, what we're going to do is we're going to factor the original expression. All right, and so what I'm going to do is I'm going to say, all right, well, this limit equals, and I'm going to continue to write the limit. All right, you're going to hear a lot about this in calculus. You need to have correct notation. Basically, you're saying the limit of this original equals the limit of this new factored form. And so what's that? 2x minus 4. And then this is x minus 4x plus 3. All right. And that's cool. That means that these two factors would cancel. And so then this limit equals the limit as x approaches 4 of 2 over x plus 3. Notice I wrote the limit again, and that's just a notation thing, and just think about it as you read it. You're saying the limit of the original must equal the limit of this new expression, which after I simplify equals the limit of this expression. And so I kind of go down the line, and now I go, hey, why don't I just plug in 4 now? And I would get, 2 over 4 plus 3, so the limit is 2/7. So in that function, or in that graph, if we were to graph it, if you went to 4, it must have an open circle, probably because that factor cancels, but the y values would be approaching 2/7 in there. All right, let's do another one here to the right. This one, oh my gosh. All right, let's just assume that if I plug in -2, I'm going to get 0 over 0. And so, why don't I factor? Well, nothing I can do in the numerator, but in the denominator, that would be, so let's see. So this is x plus 2, square root of 2 minus x. All right, and then the denominator is, oh, what a surprise, x plus 2, x plus 1. All right, so factoring is going to be a major skill for you to do. And you go, hey, those x plus 2's would cancel. So this is the limit as x approaches -2 of the square root of 2 minus x over x plus 1. And now I can just plug in. So it's kind of, we simplify it until we get to the part where I can just straight up plug in. And that's the square root of 2 minus -2 over -2 plus 1. And that's the square root of 4 over -1. So that is -2. Okay. Also, notice that I don't write limit at that last part. So it's kind of, I have to keep writing these limits until the moment where now I plug in numbers and just evaluate numbers. Okay, moving right along. You guys doing great. Again, hopefully you're rewinding the video and rewatching if things are going a little too fast, but hopefully this is going well so far. Let's go to the back side of the sheet. This is not a mistake. I actually have the same problem twice here for number 8 and number 9 because I want to show you two different techniques that we could evaluate this. All right, first off, like I said, hey, if you plug in 9, you'll get 0 over 0. So let's talk about some techniques. One technique, the one we're going to do for number 9, is I'm going to do the technique of multiplying by the, I guess I always use the word conjugate. This is a technique we've done before, the conjugate of root x minus 3. And the reason we do it is because it's a way to change the way the expression looks. So what we're going to do is we're going to multiply top and bottom of that fraction by the conjugate of root x minus 3, which is root x plus 3. So let's see what that does. That's the limit as x approaches 9. So I'm going to take x minus 9, multiply that by root x plus 3. Remember, I'm doing the conjugate over, and then the denominator is the original root x minus 3 times root x plus 3. Okay, now, man, that seems like the reverse of factoring. I'm making it more complicated. Well, let's see where this goes. The numerator, I'm not going to do anything. I'm not going to expand anything. That's just x minus 9 root x plus 3. And here's the magic, is that what's the denominator? If you were to distribute that, that would be root x times root x. That's just x minus 9. So it's kind of a weird thing. It's almost like I don't know. It's almost like we're factoring, but not. We multiplied by the conjugate. We get the x minus 9s to now cancel. And so now, again, I'm still writing the limit as x approaches 9. Now this is just the limit of root x plus 3, where I can just straight up plug in, and that's root 9 plus 3. That's 3 plus 3 is 6. Okay, so the limit of that function is 6. So now I'm going to do the exact same problem, just with a different technique. All right, so this one, instead of multiplying by the conjugate, this is just from seeing a pattern 1,000 times, and we've seen it so many times. Remember this? A squared minus b squared equals a plus b, a minus b. It's called the difference of two squares. Is that a squared minus b squared, they don't have to be nice looking squares. What we're going to do is we're going to pretend that x minus 9 is a difference of squares. So we're going to pretend, and I don't know, pretend is not even the right word. We're going to apply the difference of squares pattern to x minus 9. And so what this would do is we would just say, all right, well, what is x a square of? Well, x is a square of square root of x. And what is 9 a square of? That's a square of 3. So if you have the skills, which I know almost all of you do, you can just factor. It really is factoring. X minus 9 factors to root x plus 3, root x minus 3. And, the denominator is already the root x minus 3. So just there in one, step, we can factor, cancel, and you'll see we get the exact same answer that we did on the other side. Okay. Equals 6. All right. Cool. That was a good one. Okay. We're going to get through these last two here. I'm just about to run out of time, so I'm going to figure out a way to do this. All right. For number 10, we have a complex fraction. Complex fraction. No, you know what? I'm going to stop the video and make a fresh one in just a moment. So stopping this video.